6, so we should now start slowly, I think. Vedanga?
Yes, Siddharth, yeah. You please go ahead, yeah.
Okay, so good evening to everyone and a very good morning to the speaker. So on behalf of the Alice Star India collaboration, I welcome you all to the 5th talk of this webinar series. Today, it is our great pleasure to have with us Professor Zhangbu, a senior scientist from BNL, as our speaker. Let me also start the recording. Okay. So, on behalf of the Alice India collaboration and all participants, I convey my sincere thanks and gratitude to Professor Zhangbu for finding time for us and accepting our request. Thank you very much, Professor Zhangbu, for joining in from USA so early in the morning. So, Professor Zhangbu is a well-known physicist in our field. We all know about him. However, there are many new and young scholars. So, let me very briefly say a few words about him. So Professor Zhangbu is a senior scientist in the Brookhaven National Lab, USA. He did his BS in physics from University of Science and Technology, China during 1989-94 and obtained his PhD degree from Yale University, USA in 1999. He served as the group leader of the STAR experiment at BNL during 2013 to 19. Professor Zhangbu was the spokesperson of the STAR collaboration during 2014 to 17 and co-spokesperson during 2017 to 2020. Professor Zhangbu conducted his research on experimental heavy ion physics at AGS and RHIC at BNL. He has received several prestigious awards and academic positions such as Presidential Early Career Award for Science and Engineers for Scientists and Engineers in 2004, Kawali Frontier Fellow by National Academy of Science in 2007, Brookhaven Science and Technology Award in 2010, APS Fellow in 2011, DOE Achievement Award in 2018, and so on. On exotic particles and antimatter search, strong QED and QCD fields, and strongly decaying resonances, heavy quarks, and hadrons associated to energetic partons as probes to investigate the properties of QGP. Today, the subject of his talk is very interesting. The title is When QED, Quantum Electrodynamics, Met QCD, Quantum Chromodynamics. I would now request Professor Zhangbu to enlighten us with his words. So, Professor Zhangbu, you can now take over.
Okay, so I will share the screen now. Okay, let me start sharing. And
yes, we can see it.
Okay, good.
Yes.
Okay, I would like to thank everyone for the invitations and participate in this discussion. So, and of course, many of you, I know many of you, and as mentioned, you probably many of you also know me as well. So today I would like to discuss about when QED met QCD. And last time I was in India was 2018, and I briefly touched this topic. There has been for the last 3 years, there has been many progresses, and I would like to go through those as well. So why do I choose this title? In the later on, you will see this was inspired by when Harry met Sally, and I will tell you at the end what's the connection here, okay? So the outline of my talk will be as this. I will first discuss everything, which all the topics are everything you think, for example, related between the QED and QCD. For example, in terms of probing the quark-gluon plasma, I will only discuss about the dileptons, the chiral effect. I will also, later half of the talk, I will talk about the main thing is the Breit-Wheeler process, the vacuum birefringences, and how we can use all these probe to actually probe the properties and magnetic field in the QGP. And at the end, I will discuss a new, which we have been working on for the last year or so, the linear polarized photon collisions within the nucleon and the interference, what we observe and what it means. Okay. So as you have been working on the star or in ALICE, you know a lot of detectors, accelerator component. I will just give you an example of the burst style of the collider and detector. And this specifically is example from RHIC, but the LHC has 10 times higher energy, although it's not flexible as the RHIC, but the energy is much higher. And also the collaboration and detectors are all much bigger. So I just give you an example in this pro, show you how many different beam energies and different species we have been using to actually study QCDs, right? From beam energy of 7.7, now fixed target go all the way down to 3.8 to all the energy at RHIC for 500 GeV LHC will be multiple TeVs and different species from PP all the way to uranium. So this is give you examples of star detector evolutions as a function of year, which year we install new upgrade, new detectors, and which year some of the detectors we move out, we add the new detectors. This is very different usually from the other high energy experiment, which they will install a complete set of detectors, run for many years, and maybe do a major upgrade, run for many years. You can see almost every year we have something new input put in and response with a new species, new energies. And specifically, I would like to mention the Indian groups has built the PMDs in the early years in STAR and also in ALICE. And in recent years, the MTDs work together, collaborate on MTDs as well. So it has been very productive in addition to the physics output we discussed. In the previous lectures, you probably hear about the chemical freeze-out, chemical potentials, temperatures, which was presented in this Nature paper. Those chemical distributions, those temperature chemical potentials are all from the hygienic particle yields. And here by the Indian groups as well. You can actually measure the spectra, extracted temperatures, radial flow velocities, and these are the foundation of the input to all these data points on that point you see. So it covers a very big range in terms of BMB and also has the mainly it's because STAR has large PID coverage over the PT azimuthal range and PT, but also Collider were able to scan the whole huge range of beam energies. But by definition, when you measure the chemistries from the hygienic particles, you won't be able to penetrate into the quark-gluon plasmas. So there is another set of probe which it's more penetrating thermometers, which is the main focus on these discussions, because usually we think about the electromagnetic probe, it doesn't interact with the hadrons or quarks and all this, so that you can actually use that as a penetrating thermometers, penetrate into QGP and measure the temperatures and the properties at that particular time. And this was recently published in Nature Physics by Heather's collaborations, which using the Dilepton measurement extract from SPS and also extracted from the GSI SIS fixed target accretions, and I will go into a little more details. I need to remove one. I need to get rid of the laser, remove one so that I will be able to see the corner of. Okay, so before I go into discussing the details of Dilepton, I just want to mention the using QED or the Dilepton to plot the QGP properties is as old as the QGP definition itself. So I'm going to go into the detail now. The quark-gluon plasma was proposed in 70s, and this is one of the examples of the paper which published in 1978. And this slide was what I present at the Shuliak's 70th birthday 3 years ago. And you can see over the last, I would say over the last 40 years, more than 40 years, there have been a lot of discussions, but it's all related, also very much connected to Edwards' proposal going from using dileptons to probe the QGP properties, the thermal dilepton at SPS, the semi-coherent two-photon process, which is related to the Breit-Wheeler processes, and the vacuum birefringence, which I will talk about later, also the magnetohydrodynamics. So these are all, I will say, the topics are as old as the QGP itself and as new as any contemporary topics span over 40 years. Okay. So how does it work? This is also published by Nature Physics as comments to the Heather's paper, and how you actually can use the dilepton to actually probe the inside of the quark-gluon plasma or hadronic matter, right? As you know, when two heavy ion collide, it will create either a QGP or maybe even at a later stage or even at the beginning of hadronic matter, it can, the dileptons or the virtual photons can create from the low decays or from the resonance decays, and then you will be able to actually get the measurements at the place where all these processes happen. We know if it's a hadronic particle, when we detect it, it has to be alternate hadronization. So in some sense, it does the information at the earliest stage, but all this probe, because it doesn't interact with the QGP or hadronic matter, it actually can come out and you will be able to see it. The other, which important feature is that the dileptons, different from say, okay, other particles or the photons, is you can actually measure the invariant mass spectra, and you can measure, for example, the mu plus mu minus invariant mass or E plus E minus invariant mass, and these two spectrums are what input into the Nature Physics paper in 2018 by Harris. Why it's important is because you are measuring the invariant mass spectrum. So if you measure the spectrum slope as a function of mass, by definition, that's invariant. It doesn't depend on the boost velocities, on the blue shift, or on any other things. It still averages the whole evolutions, but it's not affected by the flow. So this is quite important because then, for example, photons, even if it comes from the early stage, but when you integrate, it actually accumulates with the flow effect, and it will get in the embedded mass. It's not depending on the flow effect, and that's why it's actually a true measurement of the temperature. It's an average temperature, but it's a true measurement of the temperature. So you can measure the slope and get the temperature. Remember, this is a SPS, the in-lam fixed target accretions. This is not as heavy as gold. This is gold, but it measure, for example, at a quite low embedded mass. So you have to rely on the model to extract it, to subtract a lot of the resonances and also the other processes as well. So as Star and Alice, we have a very different method of electron identification. So this is the DDX measurement in TPC as a function of momentums. You can see the electron band, but there is pion bands, kaon bands, and proton bands. By applying the speed of light cut, you will be able to cleanly identify the electrons. And this was done in 2003. And I feel here, I will say this is our my best accomplishment so far, because it's allowed a very traditionally hydronic detectors be able to actually become a large area coverage of the lepton detector. So what can you do this? What can you do with all these tools? You will be able to then study the chiral phase transition. We know there is the deconfinement, which you can study from the hydronic processes, the decompositions of the chemistries. But usually when we talk about the QCD phase transition, it's actually a chiral phase transition. It's not the deconfinement. So to actually be sensitive to the chiral phase transition, there are very few tools you can actually directly probe the chiral phase transition. And one of them is you are able to actually study the vector meson spectral functions by seeing how it depends on the temperatures, and coupled with the theory, you will be able to see whether you actually achieve chiral symmetry restoration. If the whole spectrum is completely disappear, of course, you assure it's chiral symmetry restoration. But even the low spectrum doesn't completely dissolve. As long as it's the same as its chiral partners, it's still a chiral symmetry restoration. But that part, you probably need the theory to confirm it. And so in 2014, Star already published a very high statistics, 200 GeV data, which clearly show a low spectral broadening only can be explained by the low spectrum broadenings. And you can even use this axis as a function of energies and centralities compared with other energies. Because it's a penetrating probe, it actually integrates the whole process. So the yields are sensitive to how long the system lasts and also how high the temperature is. So this is a very interesting and comprehensive probe. So with the BS1, which has by high statistics, we are able to actually have some measurements also in the last few years. For example, we took data on 2017, 2018. We are able at 27 GeV, 54 GeV, we are able to do this measurement, and you can clearly see the low spectrums also all show very significant broadening. One of the interesting part we are interested in is, like what I said, at the intermediate mass band range, if you see excess of the dielectrons compared with the cocktail, the hadronic cocktails, you will be able to actually use that to extract the temperature, and which will be the real temperature in before the hadronic stage, and that's actually quite interesting. This was the preliminary data results presented by STAR last year, but there are new studies coming out, so it will be very interesting to see what happened here also with the 10 roughly more data. So this will be very, very interesting to see if we will be able to measure a dependence in the beam energy scan of the true temperatures. So as you know, even in quantum mechanics, even if you have a ground state, you will actually have fluctuations. And one of the features of the QCD is in the vacuum, you will see fluctuations on the QCD, which actually have a topological charge. And this is one of the latest simulations. So you will ask, how can we actually be sensitive to this part? So there is, for the, I will say, last 20 years, there is continuous effort trying to actually study to see experimentally whether we will be there are ways to be sensitive to this. So one of the things, of course, in the AA equations, you will heat up the whole vacuums, and to observe this effect in the data, you actually need to say, okay, I need to put in the masonist fermions, the QQ bars. I also need to apply a magnetic field. And on this, you will be able to separate the charge and be able to observe some kind of charge separation, which are sensitive to these topological charge transitions. The experimental strategies to measure two-particle correlations with respect to the reaction plane. So indeed, in 2009 and 2010, STAR published a paper which showed there are significant charge separations relative to the reaction plane. So the blue is the object signs, the red is the like signs, and they are clearly separated, indication of separation relative to the reaction plane. I must say, before 2009, even 10 years earlier, in the late 90s, before the RHIC started, there are already significant studies trying to see if we have tools which can actually be accessed to this. And finally, after 10 years of analysis and figure out creative ways, we are able to actually using a tool which may be sensitive to this topological charge effect. But there are also many kinds of background which will contribute to this. And this is a slide which I took from press, which shows you have a magnetic field, which you have a reaction plane. The charge can be separated along this reaction plane. But there are also background, for example, HBT, Coulomb effect, resonance, charge conservations, momentum conservations, which will contribute to this looks like a V2 effect. And the final signal actually also need the magnetic field to exist. And the magnetic field also has orientation which not necessarily coupled with the reaction plane. So you need many different ways to try to disentangle all these background and signals. So this same effect has been, we have been trying to find different ways to actually study where the background, where the signal, what is dominant, what is subdominant. For example, we use this charge separation search as a function of beam energies, and including these results at the at HC as well. So it span quite a significant range of energies of these charge separations, and then you can try to see whether there is a place where you can see zeros, and then it will increases. And there are, you can clearly see there are significant variations. This is a very low energy data, 7.7 GeV data. The error bar is very big, but with BS2, we'll be able to reduce the error bars by a lot. There's also trying to extract what are the fractions of the signals using different methods, trying to extract what are the signal contributions in these charge separations. And at least the consensus from now is maybe the signal contribute to this charge separation we see is around 10% with a big error bars also can be consistent with zero. That's why it's very important to actually continue and see whether we have a way to decisively determine what are the contributions from the chiral magnetic effect. One of the things we do is using zirconium different charge. So if anything related to the magnetic field but not related to the QCD, it will give you a 10% effect due to the magnetic field. But if everything related to the QCD but not related to the magnetic field will be the same because their A numbers geometries are the same. And this will be allow us to actually try to separate the everything related to only the Coulomb magnetic effect and things which is purely only QCD. And this will be allow us to actually separate it. And we take the isobar data in 2018 and we try to, because the signal is small itself, right? We try to actually using a blind analysis processes. And again, this is the report last May. We have to go through many steps trying to actually analyze the data. And now we have been, for the last 2.5 years, we have been trying to go through every step of analysis. We even publish procedures how we actually do it. And as of last May, it's here. But now, although it's projection to before now, I believe we are right here. So we are very close to get the results out, which is quite exciting. So as I mentioned, to actually observe this topological charge effect, you actually need another two extraordinary phenomena to happen at the same time. The chiral symmetry distortion I mentioned. Also, the other one is the magnetic field. Okay, so the chiral symmetry distortions, we can use the raw spectra to study it. The strong magnetic field, there are quite a few tools which we may be able to be sensitive to. I will start now. I will take a detail to discuss the magnetic field, how we measure it. But to do that, I will have to start with the Breit-Wheeler processes, because the magnetic field, as you know, the heavy ions can be a source of a very strong magnetic field, because the Coulomb field, when you move at very high speed, it will create a magnetic field. But the magnetic field, if you are in a rest frame, it passes very quickly. So you need a way to actually capture it. And that's one of the important things you need to do to make sure you will be able to actually contain the magnetic field. But the first thing is to see whether there is a strong magnetic field, whether there is a way we can independently measure. So to do that, I'm going to take a detail, say how we actually can measure the initial magnetic field, and whether there are tools which will be able to be sensitive to the magnetic field at the later stage. So the detail is, I have to start with a probe. Probably you have seen the Angel and Demons say there's someone steal a bottle of antimatter from CERN and try to blow up the Venticans. The antimatter and analyze with matter to create actually explosive light with enormous energy release. So, however, can one turn pure light into matter? So this is a reverse process. And it turned out it actually has never been done. This pure process turn light into matter uniquely prove you actually done that. Right? So, however, the process actually has been calculated and proposed already in 1934. This is more than 87 years ago. Creation of two light quanta to create matter and antimatter. This is the E plus E minus. And in that paper, it says, effectively say, well, it's almost impossible to collide two X-ray or gamma ray beams at each other because the cross section is so small. Although the reverse process seems to be, you can even make a bomb out of it. The light creation process is very small, but they already proposed that by colliding two heavy nuclei with the Wavefunction photon, you will be able to realize this part. And the Wavefunction photon concept was actually proposed already in 10 years earlier and formulated in 1934. So though at that time, those are very contemporary with the discovery of the positrons. So I have briefly touched all of this in 3 years ago, which we tried to actually measure the E plus, E minus in heavy ion collisions. Okay, so the tools actually, there is a discovery in 1997, used the multi-photon light by light scattering to create E plus, E minus, and this is at Stanford, using the electrons, beam they create high energy gammas collide with multiple lasers and create the positrons. So this is considered a multiple process of the non-linear Breit-Wheeler process. And this is so far the only process which is related to the light, pure light by light creation to create matter and antimatters. There have been many proposals in the years. For example, this is using also similar concept, using also standing lasers. Remember, standing laser, it's not free laser either. All these are all standing lasers, which means you have a cavity which creates a standing laser. So in some sense, it's not absolutely pure light because the laser is not purely free colliding. The cross section is too small. There are also other extreme light infrastructure try to also create the same processes as well. Why we can actually use heavy ion collisions to actually try to create these processes is because the heavy ion collisions, when it accelerates the heavy nuclei, not only has the Coulomb field, but it also, the Coulomb field creates a magnetic field, which is the strongest in the universe so far. And this is, we compile all the possible, the magnetic field, which span 10 to more than 10 to the 30 magnitude of the magnetic field. And this heavy ion collisions clearly is one of the highest. And with this, you will be able to actually study the pure photon collisions. And this is illustrate how we actually do it. You can accelerate the nucleus. It has a Lorentz contractions. It creates close to real photons that collide. They can create, two photons can collide, or the photon can interact with nuclear, create vector mesons. So there are two processes, which one I will focus right now, and the next one I will discuss at the last point. I've discussed 3 years ago about in the peripheral gold accretions and uranium accretions when the hygienic also happens, how we actually can identify the E plus E minus pair from this process. It's a very distinct peak at the low mass. You can also see it has no hygienic resonance. For example, those omegas, phi's used to exist in the hygienic interactions going into E plus E minus channel, you don't see that at all. And this, what I present 3 years ago, is in the peripheral accretion 60 to 80%. And at that time, you compare with the starlight, you see a broadening, you see the difference between gold and uranium, and you can clearly see, compare with starlight, there's a shift, right? Atlas, a higher energy, higher momentum of the dileptons, also see a difference compared with the starlight or peripheral. And both, interestingly, both claim there are final state effects. For example, Atlas is consistent with scattering of muons in the QGP. Star, we say, well, we see the excess ER which fail to be reproduced by the starlight, right? But whether there, and this could be due to the magnetic field, which actually broadening the pair. However, when there are caveats and possibilities, the initial photon collisions, there is no reason it has to be all the same. There is no centrality. There is no reason why it has to be no centrality dependence. However, in the original star framework, or in the Wavefunction, which equivalent photon approximation, the assumption is all the photons momentum are due to uncertainty principle limited by the size of the gold, and therefore the momentum should not depend on the impact parameter. And that's why we believe very much this has to be true. Anything addition has to be final state effect, right? And even the final state effect, there are two possibilities: multiple scattering or the magnetic field. Okay. However, if you look into the details of equivalent photon approximation, is it really true that the photon PT really driven by the uncertainty principles and independent of the position momentum correlations when you actually change the impact parameters? So we spend a lot of time looking into the formulas since we are not theorists. So it's actually take a lot of time looking into the formulas and see where the issues are, right? So why the photon PT are purely driven by the uncertainty principle while there is no position momentum correlation. And it turned out it's actually quite interesting, because in the formulas, if in the traditional equivalent photon approximations, if you integrate impact parameter in 0 to infinity, you will get the traditional equivalent photon approximation where the momentum then doesn't depend on the impact parameter because you already integrate from the 0 to infinity. So the photon PT, which claim to be independent of the impact parameter, is actually completely not driven by uncertainty principle. It's all driven by the integration. You already integrate out the impact parameter from 0 to infinity. Right. So this is, instead of a physical issue, it's a mathematical issue. When you try to integrate the whole cross-section from 0 to infinity, of course, then you integrate out any impact parameter dependence. Of course, you can then try to implement ad hoc add in additional impact parameter in the cross section, but you lost the momentum part. So it's not really a physics question. It's actually a mathematical procedures. Once you disentangle it, and then you will be able to actually see the moment impact parameter dependence. And also experimentally, there are a lot of progress in the last 2 years. For example, CMS measure in UPC without hadronic interactions by looking at the different neutron emissions. They can actually see already in UPC there is no hadronic interactions. There is an impact parameter dependence of the angular distributions, and which is reasonably consistent with QCD calculation. But for example, Starlight and many other EPAs will predict there shouldn't be any impact parameter dependence. STAR also measure the UPC directions in the UPC. Remember before 3 years ago when I presented results, these are the only red point you have. Now we have the blue points, which are consistent, very consistent with the QCD, but it's very different from the Starlight calculations, which this curve is actually independent of any centralities. Okay, so this is all proof, right? The photons has a momentum distribution which is coupled with the impact parameter or the spatial distributions, and this is very important. This comes back to where the QED meet QCD. Remember in the QCD, because you cannot see gluons and quarks, so people have to invent these Wigner functions, and depending on how you actually try to integrate one part, you can have the parton distribution functions, you can have form factors, you can then decompose everything into different parts, right? But it turned out the QED also have almost exactly the same features. To find out the Coulomb distribution, the photon distribution, you also need something like this kind of Wigner distribution function to be fully characterized. The reason we don't use this is before, we always integrate out the impact parameters in E plus E minus collisions, in PP collisions, all these are integrated out, so it doesn't matter. But now we have the tools, so you will be able to actually access this. Not only we are talking about the Wigner functions in the QCD, but also Wigner functions in the QED as well. Okay. Another very important observable is if there is no momentum and position correlation, you won't be able to see any angular distributions. But we actually carry out a measurement of the E plus E minus distribution, the angular distributions, and see clearly a huge angular correlation, angular distribution of the pair PT versus the single track PT. And this also proves indeed the photons which create E plus E minus has momentum space correlations, so that you can see the coulombs, right? The Coulomb field is radially. But if you don't know the positions, all these vector directions all cancel out because you are integrate all the azimuthal distributions. But this measurement clearly shows there are probes which are sensitive to the azimuthal distributions. And this is extreme. I feel conceptually it's extremely important. I will go through the Birefringence later, but just alone, this alone, so we prove the photons created by the Breit-Wheeler concept is actually linear polarized. Experimentally, you actually can observe it. And this is extremely, I feel is extremely, extremely important, right? And this will be allow us to map out the magnetic field, right? And so you can actually have calculate all this process from the lowest order QED, which you have two Feynman diagrams. You can actually calculate. We can actually also compare with the direction distribution, refractions as a function of PT, sure, there is an initial broadening. And this can also explain Atlas's angular distribution very well as well. There is the dependence from peripheral to centers. Okay? In recent results, we also compare with the cross sections. I showed before, there is no hadronic peaks. And here with the UPC data, you can clearly see with the high statistical data, there is also no rho, no omegas, no phi's, all these peaks, because it's purely photon to E plus, E minus. The vector meson quantum number is not consistent with the two photon collisions. And this is also another proof it has to become from photon collisions. So I mentioned this direction come out. If you have magnetic field, it will broaden the E plus, E minus pairs. And these are the angular distribution or the mean PT distribution as a function of mass. Our arrow bars now are still quite big compared with the QEDs are consistent, although it's symmetrical above. With 2023 data measurement, these are the red projections. You will be able to actually have significant observables, which will be able to actually sensitive to the magnetic field. And this is another one using the cosine to find the angular distributions. Okay, so now I mentioned the strongest magnetic field exists in the universe. You have a photon going through. So why not study the vacuum birefringence, which was predicted by in the 30s and also formulated in the 50s as well, right? So you have the magnetic field, which created by the moving Coulomb field, and you have another one, which is the photon shooting at the magnetic field. So this is exactly, if you can study the process, whether it depends on the angle between the photon polarizations and the magnetic field, you will be studied the vacuum birefringence, right? Because the magnetic field is circular, the photons we know are linear polarized. So this is a perfect place to study the vacuum birefringence. Just a few words on what vacuum birefringence is, right? Vacuum birefringence means if you have a material, a light shooting through, it will split depending on the polarization. So it means its refractive index depends on the polarization of the input photons. And this is very important. I mean, conceptually, it's very simple, right? And why we can do this? Because the heavy ions, if you view one ions as creating the circular magnetic field, the other ions has linear polarized photons. So these are like a perfect place to study this kind of effect, right? But this usually in the material already observed hundreds of years ago. In the vacuum, it has never seen before, right? The only possibility is people look at the lights passing through, pulsars passing through, and see the light are polarized. This is an indirect observations and can maybe contribute to the vacuum birefringences. And that's the only experimental indirect possibility of vacuum birefringence. But for us, this is like a perfect place. There are a lot of arguments. What are the birefringence, dichroisms, optic theorems? Since, right, we try to use to prove birefringence, there is no process which in the material corresponding to this. Usually the light is energy is too low to actually create E plus, E minus, right? But if you look at any of the places which birefringence is property of the crystals which will actually spread light according to the polarizations. So I make a table, right? Just to show you why it's possible for us, right? The crystals, you can see the charge, the vacuum which created by heavy ion collisions, the charge is gold or that is close to 100. The distance to a charge where the magnetic field or electric field exists in the crystal is about Armstrong. In the vacuum, which we are trying to probe, is very close to the edge of the nucleus. The length of the material passed through in the crystal is in terms of centimeters. In the gold ions, because it's only one ion, so it's a few fermions, right? So there's the Lorentz factors, there's the photon wavelength, because for photon to shooting at such precise place, rigidity, which is proportional to this pi, is almost identical. That's why we can also realize this process. You can go through the formulas very seriously in the Maxwell equations. And if you take in the Heisenberg-Euler effect, you will be able to calculate the diffraction index difference when it's parallel or perpendicular to the magnetic field. Why it's so hard to realize this process? Because this A is tiny, 10 to the minus 24. So if you want to have a magnetic field Teslas, you have to have really big magnetic field. Even the neutron stars at 10 to the 9th, 10 to the 11th, this is also very small, right? But look at see, this is like a piece of cake, right? And so how do we compare the vacuum birefringence to actually Breit-Wheeler? So this is the Breit-Wheeler process we mentioned. Two photons create E plus E minus. If you flip this process, the two E plus E minus anion create one photon, create the other photons. And this photon, if you can observe the angular distribution, it will give you the birefringence. So again, the imaginary part, which you can effectively equivalent to cut this line, and that's why we are observing effectively the imaginary part of the vacuum birefringences. And this is what it is, right? We observe the angular distributions related to the angular between the photons and magnetic field, and that's why it's a vacuum birefringence. Their proposal in theory try to realize this process, right? A photon going through colliding with a laser field and then create a polarized photons going through, convert into E plus E minus. You can measure the angular distribution of E plus E minus. And this is, you separate all the processes in different steps, but we actually in one step realize all this process. But it's no difference. There's no difference between what we're doing and what it's doing here using a laser, right? So now we realize, I think I'm running out of time. We realize these are linear polarized photons. Why not using the linear polarized photons to collide with the gluons, right? And I mentioned the photon can collide with two gluons, create a vector mesons, create pi plus pi minus. You can also look at the angular distributions. So the imaging of the nuclei using the UPC has been done a while ago, right? This is Alice, measure the cross-section, measure the T distributions in star to actually extract the size. So this is additional. You can measure the interference between the pions coming out or the row coming out and between these two nucleons. And that's the key, right? There's another interesting interference. For example, these two nuclei, when they collide, they are separated by 20 to 40 fermions. The row, it decay in one fermi. So the row, this row never actually know there's another row exists because it already decay into pi plus pi minus. However, when you reconstruct the pi plus pi minus, you actually see an interference effect, right? And for the momentum distribution, this only exists at very low momentum. But when you measure the cosine 2 phi, it actually exists in up to very high momentum, and this is the cosine 2 phi distribution. It only exists when these two laws actually somehow, even before the decay, they know each other, they are polarized. And this is actually the EPR paradox, right? They actually know the pions is not polarized, but the law which decay into pions are actually polarized, and the pions actually know they are polarized and interfere with each other. We can even use this interference to actually measure difference between gold and uranium, and the measurements show that they are different. If you scale them in the PT directions, they are different by about 20%. This is consistent with the size difference between uranium and gold. So these are actually quite exciting. You can actually use the gluon shadowing saturations, TMDs, photon and gluons are polarized, interference, all these formula putting in to actually create the interference terms in cosine 2 phi. And this only exists, you have to assume the photons are polarized, there's a momentum distributions, and there's an interference between these two vector mesons. Okay. So there are many other examples which are actually quite exciting in the future. One of the examples which I show in the first slide is the sun, which has the magnetohydrodynamics based examples. You create a magnetic field, you interact with what the material inside create hydrodynamics. And there are also proposals on how we can actually see it using the dileptons in the QGP. But it's a hard questions, and it may be awaiting the younger generations with new ideas to actually beat down the background to actually see it, right? So with this, I would like to conclude the electromagnetic probe of new emerging phenomena in high energy nuclear accretions are very exciting. The strong QED and QCD field are very interesting and exciting field. I just give you some of the examples, right? These are some of the examples developing over the last few years, and it's quite, we are actually experimentally, I feel, right at the age of making many discoveries. So come back to the title, right? So the highly matched series, they, at the beginning, they don't really like each other. They met like in 77s, but then they don't meet with each other. They each get married. They broke up. 10 years later, they get together again, right? So the New York Times is actually mentions that it's not a question about whether they can become friends for each other, and this is quite fitting for a QCD and QED. They are in the heavy ions. The QED and QCD are actually integral part, and they are made for each other using all emerging all this exciting and interesting phenomena. It will be easier for us to do. It will be almost impossible for other fields to do. Okay, with that, I conclude. And I think I ran out of time over time. Thank you.
Thanks, Professor Zhangbu, for this nice talk. Now we open it for the questions. So if you have a question, please raise your hand or write in the chat box. Then we will take up one by one. So first I see there is a question by Aditya. Aditya, could you please?
Yeah, hello.
Yes.
Yeah, thanks for.
Yes. Do I just lost you guys or? It seems I have a hard time hearing it.
Okay, so we will come back to him. Maybe.
Or maybe he can type into the chat window, and instead of.
Yeah, he has written in the chat box. So it is related to slide number 31 about the axis leveling, is phi EE to phi e. Slide number 31.
Oh, okay. So that's the angle between between the single electron or positons relative to the pair momentum angle. So you have the E plus E minus pair angle, you have the single electron or positron angles, and this angle is the angle. So it's like, how to say it, it's similar to like spin polarization, right? You have the momentum of the pairs, you have the decay daughters relative to the angle to the parent angle. Is that clear? So the angle of the E plus E minus is the pair angle, and the phi E is the single particle angle. So this is the angle between the pair momentum and the single particle momentum.
Okay, so now we have one question from Tapanda, could you please ask?
Yeah, hi Zhangbu, beautiful talk. As always, nice to see you. I have two questions. One is I'm always intrigued by this extremely high magnetic field, 10 to the power 14 Tesla. So last year when we published this in South Korea, and the physics, the science, Eka Delson, who is the director of science and research and computing, he came to me. He says, "Oh, you are getting the same magnetic field as the LHC." So he didn't read 10 to the power 14. He read 14 Tesla. So you are creating a magnetic field which is same as the Large Hadron Collider magnetic field. I said, no, it is 10 to the power 14, not just 14 Tesla. So it was very much interesting. So the stars result and Alice result on the D mesons directed flow, and compared to the charge hadron directed flow. That's one of the best examples of, you see the QED, you have the magnetic field there, and you are dealing with D mesons and the quarks and gluons. That's a beautiful way, the way you have put up the QED and QCD at play together.
Yes.
So I would like to, this is a comment, but you can respond if you like. Yeah.
Sure. I think that's one of the very interesting results which I also discussed in the 2018. What are the different processes which can measure? Some also trying to use, for example, the lambda and anti-lambda global polarization, try to measure that, and those are very interesting results, and also those are the direction which possibly will be able to be able to measure the magnetic field. The processes are intrinsically hygienic, and whether now I think at least from although there's results, it's I don't think the theory are able to completely match with the data yet. So and the lambda polarization, that's also one of the possibilities of very interesting, that whether that will be actually be sensitive to the magnetic field. So I'm more focusing now at the initial state, and the final state you can clearly see also if you be able to the E plus E minus. What I'm trying to do is from the beginning to the end, it's purely electromagnetic effect, right? Other than the magnetic field, which can be checked by QGP with a QCD phenomena. In this process, the E plus E minus are created purely by the photons. The process which the E plus minus sensitive to are only sensitive to the magnetic field because it don't interact with the quarks. So this will be a very pure process. The only couple to QCD is by the QCD trap the magnetic field. Otherwise, it's purely QED. Right? What you mentioned there is effectively hygienic interactions, which in the QCD in the heavy quarks we scatter inside, which will have a difference in in C and CC bar, which may be due to magnetic field. That's completely possible. And I actually discussed in 2018, so I wasn't trying to repeat the same thing. But absolutely, that's a very interesting topic, which I think also deserve to compare to theory and see if there are and if they can be explained using that to constrain the field. Right?
Yeah, yeah.
And absolutely, it's very interesting topic.
Yeah, so. And my second question is, we always think that we have two different phase transitions, deconfinement and chiral symmetry restoration, chiral phase transition. You focused on chiral phase transition, yes. But you said the QCD phase transition is all chiral. Is it resolved that there is no deconfinement and there is no separation between deconfinement and chiral? They are all same? Or how can you make this statement?
Thank you for this point. When people say QCD phase transition, they always refer to the chiral phase transition. In name, the name no one means that's a deconfinement. Deconfinement is also very important. But when people say QCD phase transition, they always refer to as a chiral phase transition. In name means say deconfinement. And that's what that's what I mean. The QCD phase transition is a chiral phase transition is because that's what actually people really mean. The name mean it's referred to the deconfinement.
So deconfinement is always there anyway. Without that, you don't have even, if you have a chiral transition, you have always a deconfinement, right? So if you have a, yeah, if you have a chiral transition, that means you are producing quarks, and quarks, once, as long as the quarks exist together, they will have deconfinement, right? It's a loose term in that sense.
I don't think so. For example, the quarkonic concept is, I think it's you have the chiral phase transition and then the deconfinement. They don't need to be at the same place. One can be earlier than the other. So you have so it's not necessary they have to be. For example, the roll can still have massive mass, right? And that it doesn't need to be deconfined. So they don't need to be exactly the same place, and they don't need to have an order. They can swap over the randomly. So.
True. Thank you. Interesting. Yeah.
Yeah. But when people say QCD phase transition, it's really what they mean is the chiral phase transition.
Yeah. Yeah. Yeah.
Okay, so we have one more question. Pratek, could you please unmute and ask?
Hello. So I want to ask that what do you expect on the presence of this chiral phenomena at LHC energy as compared to the star energies? I am asking is because though the magnetic field at LHC energies is approximately of the 10 times larger than that star, but it decays also very faster as compared to star. So could you please let me know that what is the expectation? Do we expect this chiral related phenomena at LHC energy to be present or not? Because magnetic field decays at a faster rate.
That's why. So I feel you know as much as I do. I think it's no one really make a different predictions of what how long the magnetic field lasts, right? Because to have this effect, you really have to have something trap the magnetic field so that it lasts longer. The magnetic field in the vacuums cannot create the chiral magnetic effect. They just decay too fast, even at the RHIC energies. Right? So you always have to have something else which be able to keep the magnetic field, trap the magnetic field to be able to say I have a CME effect, and how much the field can be trapped at RHIC or LHC, no one really know the answer. Right? So in some sense, it's more like experimental driven research than the theory-driven research. That's why it's important, like what Tapan said, that you measure independently using the D bar V1 difference, you're using this Breit-Wheeler processes, using global lambda polarization to independently measure the magnetic field. That's very, very important to do, right? Because no one, I don't think there's any theory prediction say, hey, I know exactly how much the field can be trapped, right?
Thank you.
Does that answer your question?
Yes, yes.
I mean, the answer is no one knows, right?
Okay, so now we have another one raised hand, Professor Vedanga Das Manti. Vedanga, could you please ask?
Yeah. So, Zhangbu, you talked about Breit-Wheeler process, but there is also something called the Bethe-Heitler process, where a real photon collides with the electromagnetic field of the nucleus. How is it different? I mean, how do we know one or the other?
That's right. So this is a very important question because, how to say it? I mean, those processes, once it formulated, it immediately was discovered because why? It's easy, right? And because you can shoot a photon into a fixed target and see it, right? Because the Coulomb field is stationary. In terms of formula theory, right? You can calculate what is the virtuality determine this process, right? And in the paper which I really went through is in 1993, that paper which actually be able to determine, say, when you are in photon energy omega divided by gamma, this, let me maybe share the screen so that it's easier to explain it. Let me, so, okay. I will try to share the screen. It also has to be big enough to not dominate by the virtuality. So it has to be a sweet spot.
I see.
Right? So they actually can formulate this paper, which I mean, it's a theory paper, even often very hard to understand. And this paper actually formulated clearly what are the conditions to be a two photon collisions.
Okay. Okay.
Right? And the key is this, right? This term has to be much smaller than the photon omega itself. That means the gamma has to be big, but it also has to be big enough so that it's not dominated by the virtuality.
Okay.
And it's very, very clearly laid out in that paper. That's why I feel that paper is actually very useful to go through. And it's actually quite interesting to read. So.
One last thing, can we get constraints on the magnetic field reached by this measurements?
I think, I believe so. From what we measure, we limit to, I mean, our measurement need to set a limit about 14 MeV. Okay, from the direction broadening compared with the model, about 14 MeV. This is about maybe a factor of 3 smaller than the peak value of the magnetic field. So that means if there's any times smaller than the actual peak value of the magnetic field from what we have now.
So we can put a lower limit, or it will be up.
Now we can put an up limit, but if you measure error bar to be small, then you can put the screen again and show you where that is. So let me share the screen. So this part, right? Now,
okay.
compare with model, now it's about 1 sigma, right?
Yeah.
So you can only set the upper limit, so it cannot be bigger than 14 maybe, which is equivalent to about 3 times smaller than the mechanical. But if you measure to be error bar to be much smaller and it's consistently away from the mode theory QED calculation, then you can set a low limit.
Okay.
Right? But if you measure the central value also closer, then you still only be able to set a up limit, but much smaller up limit. Right?
Okay. Yes. Thank you, Zhangbu, for the nice talk.
And but then the other one which is compared with the better head process is this process, right? 2 real photon cannot create the vector meson.
Yeah.
But 1 real photon, 1 virtual photon, you actually can create a vector meson. This is quantumly allowed, right? Because real photon doesn't have zero helicity, but virtual photon has, and we clearly don't see it.
Okay.
Right? Not only just from the formula, but experimentally, one of the main points is you can actually prove it, right?
Okay. Thank you.
Okay, so see any more raised hands? So speaker, Professor Zhangbu, thank you so much.
Ask one question? Can I ask one last question?
So Tapanda.
That.
Yes, sir. Please. Yeah.
Okay. Thanks, Professor Su, for a nice talk. This is really new information to us, particularly to me. So we know that this is a well-known process in astrophysics, this Breit-Wheeler process. Now, just one question I would like to know from you is that we know that the probability of a gamma-gamma collision to give electron-positron pair is very small.
Yes.
And for that matter, you need actually some kind of, gamma laser to get this electron-positron pair to be produced. My question is, in an event-by-event analysis, how one can expect enough number of, say, electron-positron pairs that are being produced from the gamma ray that might be created in a collision, particularly at star energy.
Yeah. So I will say the answer is I will say relatively. I mean, to answer it very simply is say because the ions actually can come very close, right? The ions can come very close to 20-40 female, and that is very different from if you are shooting 2 lasers together. Or you can make the laser shooting at each other very close to each other, but you cannot arm at the micron, at the Fermi scale, right? Because even you are able to shoot 1 photon to the other photon at female scales, that's only 1 pair. But when you shoot at the female scale for the 2 ions, those are a lot of photons, right? That's why it's proportional G to the 4th power. Even if you just shoot 2 ions at each other, effectively you are shooting a bunch of lasers at each other at the fermion scale. if you prepare two lasers, when you shoot at each other, when you are able to come this close, it's also only one pair at a time. Right? That's why you don't have this G to the 4th power enhancement. That's 10 to the 8th power. And that's the biggest difference, I feel. That's that. I don't know whether that intuitively answer your question, but that's, I will say how I explain why we can do it, and the laser can, two high energy gamma rays can never do it because of the cross section, because of this G to the 4th power enhancement.
Okay, okay, if I understand. Thank you.
Okay, I think so. We thank the speaker again, Professor Zhangbu. Thank you again for your time.
Thank you very much.
Nice talk and followed up discussion. So we had a lot of discussion. So we overshoot the time a little bit, but this is fine. In webinar, it is okay.
Yeah, sorry, my talk is kind of too long. So
fine. In webinar, it is okay. It is allowed. So I thank all the participants also for joining in. And we close the session. See you sometime in India in person.
Thank you very much. And
Bye-bye.
I'm looking forward to it.